What's the difference between an element, an atom, an ion, and an isotope? To answer this question, we must recognize that subatomic particles, protons, electrons, and neutrons, are the building blocks of all four of these substances, and that all three of them have a certain amount of mass and a certain amount of charge. Take special note of electrons' mass of 0 in quotations. It's not actually a zero mass, it's 0.0005 atomic mass units, but it's so tiny that we essentially treat it as if it were zero. With that, a great starting point to deciphering between these four is choosing the one that's the odd one out. And that happens to be element, because it's the umbrella category. An element is defined and distinguished by its number of protons. Atoms, ions, and isotopes are all different versions of the same element. And here's what I mean by that. Here is the periodic table of elements, and it's what we know as hydrogen, carbon, oxygen, etc. These are all completely different elements, and we'll single in on the element of oxygen. If we look at its elemental box, it has an atomic number of 8, meaning that it by definition will have 8 protons. If it doesn't have 8 protons, it's a completely different element. In other words, atomic number is unique to each element. Likewise, because atomic number and number of protons are the same thing, they equal each other, they are said to be interchangeable. In math, to interchange is to substitute one variable for another because they're equal to each other. In this case, x and y are interchangeable. Thus, we can substitute x for y so everything is in terms of a single variable for which we can then solve. Just like in math, where variables can be interchanged because they mean the same thing, in chemistry the atomic number and the number of protons are interchangeable. So when we say oxygen has an atomic number of 8, that also means it has 8 protons, and that's what defines and distinguishes oxygen. In other words, having 8 protons is what makes something oxygen. Every form of oxygen element, an atom, ion, or isotope, always has 8 protons. That never changes. And this rule applies to every element on the periodic table. Each one is defined by its unique number of protons. Oxygen is 8, hydrogen is 1, nitrogen is 7, and so on. So with that said, what exactly is the difference between an ion, atom, and isotope? We'll take this one at a time. An atom is a type of an element wherein the number of each subatomic particle is usually the same. In other words, the amount of protons in the element equals the number of neutrons, which equals the number of electrons. More simply, to be considered an atom, all that matters is that protons equals electrons. Neutrons don't factor into the definition of an atom. With that, what's the charge of an atom? For reference, charge of a substance equals the number of protons minus the number of electrons. Likewise, remember that an atom is defined as an element with an equal number of protons and electrons. And we've also discussed the fact that when two variables are equal to each other, they're interchangeable, meaning that we can substitute one for the other. So if protons equals electrons, then protons minus electrons equals protons minus protons equals 0. Therefore, all atoms have a neutral charge. And you can test this out with different types of atoms. As long as it's an atom, there's going to be the same number of protons and electrons, and any number minus that same number is going to be 0 by definition. Hence, why each atom will have a 0 charge. So the key takeaway, what makes something an atom is equality between protons and electrons. Neutron number may vary, but that only matters when we talk about isotopes. With that in mind, which of these subatomic count combinations does not represent an atom? A, B, or C? Very simply, we go back to the definition of an atom and we see that the last one is the only one that's not an atom, because the number of protons and electrons are not equal, so scenario C doesn't fit the definition of an atom. So if we go back to the element of oxygen, what would that look like for an atom? We know that the number of protons and electrons are equal in number, but what exactly is that number? Is it 2 equals 2? Is it 100 equals 100? Are there multiple pairs of numbers possible for an atom of oxygen? The only pair is 8 protons and 8 electrons because oxygen's identity is locked to 8 protons. Therefore, an atom of oxygen must have 8 protons and exactly 8 electrons. And this works for each element of the periodic table. An atom has an equal number of protons and electrons, and that number for which they are equal is determined by the atomic number found on the periodic table. For oxygen atoms specifically, the neutron count may sometimes match the proton count, or it may not. Neutrons can vary and do, but that's when we talk about isotopes. Make an atom of nitrogen with appropriate numbers of each subatomic particle. How many protons, how many neutrons, and how many electrons do we have? Well, the correct answer is that we have 7 protons, 7 electrons, and neutron count is any positive number. Because as I mentioned, for the definition of an atom, the number of neutrons doesn't matter. Does this combination of subatomic particles fit the definition of a nitrogen atom? Technically, yes, it does. Is it realistic to have 70 neutrons, 10 times as many neutrons as protons? No, that would be far too unstable to exist in nature, but nonetheless, definitionally speaking, it is an atom. So we've explored the ins and outs of atoms, but what about the other two forms of an element, ions and isotopes? An ion specifically is any element wherein the number of protons and the number of electrons is not equal. So atoms and ions are opposites in this sense. If protons equals electrons, it's an atom. If protons doesn't equal electrons, it's an ion. They cannot both be true at the same time. This is just like flipping a coin. Whenever you get a heads, it can at the same time be tails and vice versa. Furthermore, you must get a heads or tails, as there's no scenario where it's neither. So no matter what combination of subatomic particles we have, our element will either fall into the atom or ion categories. An atom if protons equals electrons, an ion if protons does not equal electrons. Those are the only two possibilities, and there's no scenario where it's neither. For oxygen specifically, because it must always have 8 protons, to be an ion, the only number of electrons it cannot have is 8. So it could have 6, 7, 9, 10, usually something close to 8, but never exactly equal to 8 if it's an ion. And as with atoms, the definition of ion makes no mention of neutron count. So again, in theory, it can be any positive count of neutrons. So we've established counts of protons, electrons, and neutrons for what constitutes an ion, but what about the charge of an ion? If you recall, charge is the number of protons minus the number of electrons. This is because a proton has a +1 charge and an electron has a -1 charge. Likewise, remember that all atoms have a 0 charge because a number minus the same number, 5 minus 5, 10 minus 10, will give us 0 every single time. Ions, on the other hand, are defined by an unequal number of protons and electrons. So if we calculate the net charge for one of the ions presented earlier, it would be 33 protons minus 34 electrons, and thus a -1 charge overall. And that makes sense because we have one more negatively charged particle than positive, so the negative is going to take over by 1. Analogously, I made $33 and lost $34, so I'm in the hole by $1. Compare that to an atom where it's like making $30 and spending exactly all of those $30, so you end up with $0. Therefore, because ions by definition have an unequal number of protons and electrons, all ions will have a non-zero charge. And going along with our theme of ignoring neutrons, neutron count also doesn't matter for calculating the charge because it doesn't show up in this equation. And very simply, this is due to the fact that neutrons don't have any charge, so it doesn't contribute any charge to the element no matter how many there are, because 0 plus 0 plus 0 plus 0, etc., will always equal 0. So isotope is the only one left. The thing that's really interesting about this is that an isotope is simply a version of an element where the number of protons is fixed, that's what makes it the element, but the number of neutrons can vary. The word fixed means that it doesn't change. And for each element, we only have a single specific number of protons, and variable neutrons as in it can change / be different. So as an example, let's look at some isotopes of carbon. For carbon and carbon alone, there will always be 6 protons, but there's a wide variety of what neutron counts could be. We can have a carbon isotope with 4 neutrons, with 5 neutrons, 6, 7, etc. So really we can say that an isotope is an element with any number of neutrons. But how exactly does this definition of isotope fit in with the existence of atoms and ions? Remember, we mentioned earlier that no matter what combination of subatomic particles our element has, it must either be an atom or an ion. As I said, this is just like flipping a coin. When we flip a coin, it's either going to be a heads or tails, and there's no other outcome. Analogously, an element is either an atom or an ion. There will never be an element that won't be either of these two categories. In other words, atoms and ions already account for 100% of all elements. But what does that have to do with isotopes if atoms and ions already comprise all elements? Well, an isotope just adds another layer of information by specifying how many neutrons that element has. But every isotope is still neutral atom or charged ion. Each of these P-N-E combinations we labeled earlier, either as an atom or an ion, depending upon the balance of protons and electrons, is simultaneously an isotope, because we're acknowledging exactly how many neutrons it has. Let's single in on our hydrogen isotope with 3 neutrons. We know it's hydrogen because there's 1 proton, and it's an ion because protons and electrons are not the same. This particular isotope of hydrogen is called hydrogen 4. But where exactly are we getting this 4 from? Well, the number after the dash equals the mass of the isotope, and it's the sum of the protons and neutrons. Think about it. A proton and a neutron each weigh 1 atomic mass unit, and remember that an electron's mass is so close to 0 that we treat it as such. So we're going to ignore the electrons, and if we have 1 proton and 3 neutrons, the total mass of our hydrogen 4 isotope is 4 AMU. And a very small distinction to point out. 4 atomic mass units would be the mass of the isotope, whereas 4 would be the mass number, in other words, the number of protons and neutrons. Very simply, whatever the mass number is, isotopic mass is that same thing but with an AMU. This is because mass number is the sum of all the protons and neutrons, and isotopic mass is the mass of all those protons and neutrons. So if we revisit our isotopes of carbon from earlier, you can see how it connects together. Each has 6 protons because it's carbon, and the different neutron counts lead to different sums and masses overall. So with that said, how many neutrons does iron 54 have? Well, if carbon 10's mass number is 10, carbon 11's mass number is 11, and carbon 12's mass number is 12, iron 54's mass number is 54. And we've already established that mass number is protons plus neutrons. And the atomic number tells us that we have 26 protons. So we plug that in, we substitute that into the mass number equation, do a bit of algebra, and get that there are 28 neutrons for this particular isotope of iron. Mass number is a 3-variable equation, so we can rearrange this equation to solve for any one of the 3 variables given the other 2. And solving for n, just like we did, is more or less the basis of the isotopic notation, where we put the chemical symbol in the middle, the atomic number in the bottom left, and mass number in the top left. So how do we convert each of these isotopes from earlier into isotopic notation? It doesn't really matter how we start, like the order that we do, but we may first want to start by putting the mass number on the top, 11, 4, 15, and then put the chemical symbol there and the atomic number in the bottom left corner. What about this isotope? How do we convert a combination of protons, neutrons, and electrons into isotopic notation? We'll take this one at a time. Scandium is the element because 21 is the atomic number, and we can look at the periodic table, and that's how many protons we have, so that's the atomic number. So we're going to put it in the bottom left corner. And the mass number, 42, is the sum of the protons and neutrons, 21 plus 21, so we have all 3 components. However, we are not done, because this is simultaneously an ion in addition to being an isotope. And since it has one more proton than electron, it has a positive 1 charge, and we must indicate that in our notation. Therefore, complete isotopic notation includes the chemical symbol, the atomic number in the bottom left corner, the mass number in the top left corner, and the charge in the top right corner. Each of these, respectively, communicates how many subatomic particles our element has. The atomic number is the number of protons, 42 in this case. Neutron count is 50 because 92 minus 42, mass number minus atomic number, and the positive 2 charge tells us that there are 2 fewer electrons than protons. So did you learn the following? 1. Element is the umbrella term that covers atom, ion, and isotope. 2. An element's identity comes from its proton count, the atomic number. 3. Protons versus electrons determine whether it's an atom, neutral, or an ion, charged. And don't forget that net charge equals protons minus electrons, meaning that all atoms have a 0 charge and all ions have a non-zero charge. 5. An isotope is an atom or ion with a neutron count specified. 6. Each isotope has a mass number, proton plus neutrons, and a matching mass in AMU. 7. Isotopic notation combines it all. Bottom left is atomic number, i.e. protons, top left is mass number, protons plus neutrons, and top right is charge, protons minus electrons. And in the end, it all comes back to the mass, charge, and identity of the 3 subatomic particles, protons, neutrons, and electrons.